So, hello everybody, welcome back to the beginning of our discussion of the two really important cellular biochemical pathways that we need to discuss this semester. The first one being, in this presentation, cellular respiration, and then following up in the next one, or the next module, the discussion of photosynthesis. These are two biochemical pathways that are intimately connected together. And as part of the introduction to cellular respiration this morning, I'll quickly go over that connection. It should be a reminder to you because we've already talked about this in the past, but it never hurts to go over it yet again, just to make sure that everyone is aware of that connection. So one of the things to realize is that these two biochemical pathways are pretty complicated, and they bring to the table, or they require us to bring to the table, everything that we've been discussing so far this semester, starting with chapter 2 all the way through to chapter 8. All of the concepts, all of the ideas that we've been discussing in those chapters now come into play in understanding chapters 9 and 10. So I'm going to try something a little bit different with the cell respiration presentations, in that rather than do it in one long presentation, I'm going to break it up into some smaller chunks, hopefully no more than about 30 to 45 minutes long for one or two of the longer ones. Internally, some of the longer ones will even be broken up into smaller sections because I've got some concept checks in there, and some of them come up reasonably quickly after a very short discussion. So I don't want to break them up into really, really short videos, but I'm trying to avoid having some of those long videos or presentations that we've had up till now. And I'll be really interested in getting some feedback from you on which approach you prefer. One single long one with the concept checks where you can break and come back whenever you want to, or a number of shorter ones that you can watch as individual presentations. The thing will be, and this I am acutely aware of, that the sum total of all of these small ones is probably going to be close to what a single long one would be. So in terms of time, actual physical time spent watching the presentations, there's probably not going to be a whole lot of difference, but it should be a little bit, well, we'll see. I don't want to prejudge what the situation is going to be. I'll break this one up into those smaller videos and provide links for them in the chapter overview, in the weekly overview this week, and we'll see how we get on in terms of your understanding and your which approach you prefer to be used in the future. I will take your responses and follow what you tell me is your preferred way of approaching the information. One single long presentation or a number of shorter ones that add up to essentially the same amount of time, but a number of animations rather than a single, or video rather than one single long one. The other thing I want to point out is that by the time we get to the end of this week, we will be at the end of week 6, and we'll actually be halfway through the semester. So we have essentially reached that midway point of the semester. So there is an exam at the end of this week. So it's exam number 2, which is appropriate because, again, it's the midpoint, and that's the second of the 4 exams that we are going to do as part of the module approach. The last 3 chapters will be rolled into the final exam and will be covered only in the final exam. Or the questions relating to those chapters will only be in the final exam. So we've got 4 exams, and so we'll be doing exam 2 at the end of this week. And you'll be, we'll be halfway through the semester for this semester. So that's something to bear in mind as well. If you have received a message from me regarding your result from exam 1 and an invitation to come and talk to me in office hours about where you're at so far this semester, by all means consider doing so. I will be available for office hours and would welcome your visit and the opportunity to help you figure out how to approach the rest of the semester so that you can do better and successfully complete the semester with a grade that you can be proud of. Anyway, just a little bit of housekeeping so that, yeah, just a little bit of housekeeping. Let's just leave it at that. So let's move on with taking a look at cellular respiration. So let's take a look at this first section. So in this first section, we're going to talk a little bit about what cell respiration represents, what the connection is between mitochondria and chloroplasts. And we're going to talk about some specific features of the chemical reactions that are involved in both cell respiration and photosynthesis. So some of the ideas that we're about to encounter in this first section are going to translate into the next chapter as well, because not surprisingly, perhaps, or maybe surprisingly, the types of chemical reactions that we're going to encounter here in cell respiration in a general sense are going to be the same types of chemical reactions that we're going to encounter in photosynthesis in the next chapter. They're not specifically identical reactions. There are different sets of reactions in each process, but in terms of the chemical concepts that are involved with these chemical reactions, they are of the same type. So once we discuss the types of reactions that are going on here in cell respiration, you need to make sure that you bring that knowledge with you to photosynthesis in the next chapter. So there is this connection between cell respiration and photosynthesis. And we've talked about this before, the notion that energy flows linearly through ecosystems. So it flows in to the ecosystem via photosynthetic organisms, primarily plants and algae. But we've seen that there are other types of photosynthetic organisms, and they use the energy of light to turn carbon dioxide and water into different types of organic molecules. And we typically think in terms of glucose, but we could add in there any type of organic molecule that you can think of that is an organic molecule found in life, because plants are the primary organic chemists of life. They incorporate carbon dioxide into all types of organic molecules. Animals and other organisms that then cannot carry out photosynthesis in some form are then dependent on those organic molecules as a source of energy and raw materials. And the most efficient way of accessing both the energy and the raw materials is via the process of cellular respiration. Now, not all organisms do all parts of cellular respiration, as you'll see. But there is a part of cellular respiration that is considered to be universal, and that tells us something about the origins of cell respiration. And we'll touch on that a little bit before we're finished with this chapter. But we also need to bear in mind that it is the second byproduct of photosynthesis that turns cell respiration into its most efficient form, and particularly its most energy efficient form, and that is aerobic respiration, cellular respiration in the presence of oxygen. And that requires, in the case of eukaryotes at least, the presence of mitochondria as well, because the cellular pathways, the biochemistry of the aerobic part of cell respiration lies within the mitochondria. And we've talked about the origin of mitochondria as an endosymbiont of an aerobic bacterium by an early eukaryotic cell. And so we also see the role of oxygen in aerobic respiration as carried out by bacteria. But then we also need to recognize that there is anaerobic respiration, that is cellular respiration, or a form of respiration that is carried out in the absence of oxygen. And there are two basic types of pathways that we can address there, and we will talk about those towards the end of this chapter when we address what happens when you don't have oxygen. But our primary focus at the beginning is all about what happens when oxygen is present. So let's move onwards and see what is involved in this process of cell respiration. So one of the things that we do need to bear in mind is that because it's the primary way of carrying out cell respiration is in the presence of oxygen, it is not a bad analogy to think about it as a burning process. Unfortunately, when we think about burning, however, we think about the complete degradation of the fuel and the release of carbon dioxide and oxygen and a whole bunch of heat in a very intense chemical reaction that we call fire. Or if we're thinking in terms of the car analogy that we were talking about in the previous presentation, a small explosion or a large explosion that we contain within the body of the car engine. Either of those two ways of releasing energy don't work particularly well for cells because it results in the release of a whole lot of energy really, really quickly. And one of the things that I often do when we start talking about the release of energy, and you'll see this outlined a little bit later in another diagram, but I want to introduce you to this concept right now, is the notion that there are a number of different ways that you can get energy out of chemical reactions. And we can think in terms of the playground slide that I introduced you to in the last presentation as a way of illustrating this. So let me draw a couple of, oops, let me start this up again and let's see if we can get this to draw this time. I'm not sure why I can't draw today. Because I had it set on white. Okay, let's try this again. Okay, so here's our axis. And it's possible to draw a representation of a slide just by doing this. So here's two slides. And if I was doing this in the classroom, I would typically label these slide A and slide B. And the question that I would ask at this point is, which of these two slides would result in the release of the greatest amount of energy? And I could let you think about this for a minute or two. And the chances are really good that the vast majority of you, if I could ask you to do a show of hands as to which slide you think releases the greatest amount of energy, the vast majority are probably going to pick slide A. Some of you might pick slide B. Now, the reason why you've probably picked slide B is because slide A is because it's the steepest of the two slides, and it stands to reason if it's steep, it's probably going to release the greatest amount of energy. Those of you who pick slide B, you probably are thinking in terms of the fact that it's not the steepest slide. So maybe because you take a little bit longer to get down the slide, you might be able to harvest a little bit more energy out of it. The reality is that both slides release the same amount of energy. And the reason why is because your starting point is here and your finishing point is here. And therefore the vertical descent is the same, irrespective of which slide you go down. So both slides actually release the same amount of energy. What is different is the rate of release. So when we think in terms of the playground slide, or we think in terms of a chemical reaction, and we think in terms of the delta G, amount of free energy that's released by the reaction, the vertical distance remains the same, irrespective of how quickly the reaction is occurring. It's really all about the rate at which the energy is being released. So on slide A, because you're traveling faster, clearly you're releasing the energy much faster. The rate of release is faster. In slide B, because it's not as steep, your speed is not as great, so the rate of release is slower, but the distance you go down vertically remains the same. So the actual energy release remains exactly the same. And for a cell, it turns out that neither of these two options are particularly great, because once you start sliding down, you're essentially committed to going all the way to the bottom, and therefore you're committed to releasing all the energy all at once. And the problems for a cell is it cannot handle that large amount of energy all at once. It prefers small packets of energy. And so there is a third option. And remarkably, you are familiar with this, although you may not realize it. So let me change the color. Here is the third option. This is option C. And yes, you may laugh at my diagram. Go right ahead, have a good giggle about it. But option C is a staircase. And the advantage of a staircase is the vertical distance that you go down, it's still the same as for slide A and slide B. So the amount of energy that's released in going down the staircase remains exactly the same. There's no change in the energy release. It's exactly the same because the vertical distance remains the same. But it's controlled because you go down in increments. And therefore the energy release is in small increments. So the sum total of the energy release going down all of the steps remains the same as the energy release going down slide A or slide B. But it's a controlled release in small increments. And that's great for cells because cells can handle that. And as you'll see, as we talk in more detail about cell respiration, there really is a step in cell respiration that occurs in the mitochondria that looks a whole lot like a chemical staircase, where something passes in a stepwise fashion through a sequence of processes, through a sequence of chemical reactions, in fact, that resembles the movement of someone down a staircase with an incremental release of energy. And so thinking in terms of the staircase is a good analogy to thinking in terms of the way a cell goes about releasing energy. I'll just put a note in here as the staircase represents a controlled incremental release of energy. And the amount doesn't change. It's the vertical distance. It's the same. So this is why it's really important to think in terms of energy release through this series of chemical reactions that we refer to as cellular respiration in terms of a staircase approach, an incremental, very controlled release of energy. And you're actually going to encounter along the way a process that really does look like a cellular staircase. So I wanted to introduce you to this concept right up front because it does influence how we start to talk about cell respiration, because it starts to influence how we look at the chemical reactions that are taking place here. So here is the overall chemical equation for cell respiration. C6H12O6, that's glucose, plus oxygen gives carbon dioxide, plus water, plus energy. And this is an equation that you need to know. You ought to be able to write this out from memory. You ought to be able to write this out blindfolded. You ought to be able to write this out without even having to stop to think about what is the equation for cell respiration. It should be second nature to you. Glucose plus oxygen gives carbon dioxide and water. And it really does explain, chemically at least, what is happening as part of cell respiration. We are going to chemically disassemble glucose. And the net end product of that chemical disassembly is going to be the carbon dioxide. But as we chemically disassemble the glucose, we need to be able to extract energy out of it. And the question becomes, how do we extract energy out of glucose through a series of chemical reactions? And the answer comes down to electrons. It's all about the electrons. It's all about extracting electrons out of glucose in such a way that we can extract energy out of them. So what we're going to see is that the series of chemical reactions that represent cell respiration, particularly those chemical reactions that represent the chemical disassembly of glucose, but also some of the other reactions that involve the electrons that we're extracting out of glucose. There's going to be a constant shuffling of electrons, moving electrons from one molecule to another, or at least the appearance of moving electrons from one molecule to another. And that means we have to have a way of describing this chemically. And so chemists have come up with two terms, oxidation and reduction, to refer to this transfer of electrons. So oxidation is one part of the transfer, and reduction is the other part of the transfer. So oxidation represents the loss of electrons, that part of this transfer of electrons. So a molecule that's involved in one of these chemical reactions that gives up electrons is said to be oxidized or undergoes oxidation. A chemical that then receives those electrons is said to be undergoing reduction and is referred to as being reduced. Now, it's really important that you understand these two terms, oxidation and reduction. And there are two separate ways that I have of allowing you to learn these two mnemonics that allow you to make sense of these two terms. So I'm going to write them out here for you. And that means that you can start putting them into practice, learning them and figuring and remembering what each of them means. So there's one that I really like and one that works, but it's not the one that I really like. So let me give you the first one, which is, let me make it work here, oil rig. And that is oxidation is loss. And if you want, of electrons. And reduction is gain of electrons. So that allows you to learn this connection between oxidation and reduction. Oxidation is loss of electrons, reduction is gain of electrons. And this one works. If you like this one and it works for you, then by all means go ahead and use it. The one that I really like, however, is, and I'll change color on this one. Leo. And the reason why I like this one is because it's a little bit easier to remember, because Leo, the lion, goes grr. So it sort of makes it, I mean, it's cute, it's a little funny, but it gets to the point. Leo, the lion, goes grr. So Leo, grr. So loss of electrons. Oops. Let's erase that. The E in, we've already got it. Loss of electrons is oxidation. Gain of electrons is reduction. So you can use either of them. You can learn both of them. It's up to you. Just make sure that you understand what oxidation and reduction actually refers to. Now, in some cases, oxidation and reduction literally means an actual transfer of electrons. And we've seen an example of this already when we were talking about ionic bonds in chapter 2. The origin of an ionic bond in the case of sodium chloride is in fact the product of an oxidation reduction reaction. So let me show you that example. Here it is. Here's sodium. Sodium, remember, gives up an electron. It's weakly electronegative. It has a single electron in its valence shell. It wants to get rid of that electron, so it's more than happy to give it up, but that's losing an electron. So chemically, that's an oxidation process. So the sodium is oxidized. The chlorine, remember, has 7 electrons in its valence shell. It desperately wants another electron. It's electronegative enough to capture that electron from sodium, so it gains its electron to become the chloride ion, but it has gained an electron, so chemically that's a reduction. So the sodium has been oxidized and the chlorine has been reduced. And so you've got a literal transfer of an electron from one to the other, and you've got a reduction and oxidation couple, or a reduction and oxidation pair. Now, one of the things that you're going to hear me say over and over again as we talk about reduction and oxidation reactions is that you cannot have one without the other. You cannot have a reduction without an oxidation, because if you're going to add an electron to something, that electron's got to come from somewhere. It can't magically appear. And if we remember that electrons actually represent a source of potential energy, we also have to throw in there the first law of thermodynamics, which remember says energy can neither be created nor destroyed. So electrons as a source of energy cannot magically appear to do a reduction, nor can they magically appear as part of an oxidation. They have to come from somewhere. So something has to give up an electron in order for something else to be reduced. You cannot have one without the other. So let me add that in here. So you can't have one without the other. And that's the reason why we often refer to these as redox reactions or redox couples, because one of these is always connected to the other. You cannot separate them. If something is going to be oxidized, something has to carry out, it has to be reduced in order for that to happen. So much so that we do have names for these chemicals. Something that accepts an electron is said to be an oxidizer. Why is it an oxidizer? Because it's taking electrons away from something, and that results in that something being oxidized. So chlorine is described as an oxidizer. So the fact that chlorine grabs that electron from sodium means that the sodium winds up being oxidized. So chlorine is described as an oxidizer because its presence is what results in the sodium being oxidized. By the same token, however, sodium So sodium is a reducer or reducing agent. Chlorine is an oxidizer or an oxidizing reagent. So these are terminologies that you also have to get used to using and hearing, because these are frequently used in describing these sorts of chemical reactions. If you've ever seen a truck that carries chlorine for pools, you'll see a big tag on the outside that says warning, oxidizer. That's because of the presence of chlorine. Because chlorine is an oxidizer, it will grab electrons away from other things. That means it itself becomes reduced, but it means whatever it stripped the electrons away from has been oxidized. Hence, chlorine is an oxidizer. Likewise, sodium is a reducing agent or a reducer for the same reason. So this is what happens when you strip electrons, when you physically strip electrons from one thing and add them to something else, a literal transfer of electrons. And that gives rise to the ions that give rise to the salt crystal. It's a redox reaction. When we think in terms of molecules that are linked together by covalent bonds, shared pairs of electrons, the situation is a little bit more complicated in terms of recognizing oxidation and reduction. But nonetheless, it does happen, and it's really important because this is the explanation of oxidation and reduction in cell respiration, and it's something that we really need to be aware of. So let me give you another example of an oxidation reduction reaction, but in this case, it's all about covalent bonds. And remember, covalent bonds are all about sharing electrons. So we can't really think in terms of physically moving the electrons from one atom to another, not in the sense that we saw with sodium and chlorine. But nonetheless, we can talk in terms of changing the energy environment of the electrons. Now, why would that be important? Well, if we come back here, we need to remember the nature of the relationship between sodium and chlorine. Sodium is weakly electronegative, chlorine is strongly electronegative. So any electron associated with sodium is freely given up because sodium doesn't hold on to it very strongly. That's the whole concept of electronegative. And because electrons represent potential energy, when sodium gives up its electron, it's literally giving up energy. You may not have thought about it that way, but it's giving up energy, which means that we can also think of oxidation as being an exergonic reaction. The exergonic reactions we saw in the last presentation are reactions that release energy or make energy available. So if you give up an electron, which represents potential energy, then you're not only being oxidized, but you're giving up energy, which means you're carrying out an exergonic process. Likewise, chlorine, being strongly electronegative, is grabbing that electron and it's moving it into a situation where that electron is not so freely available anymore, because chlorine is going to hold on to it very, very tightly. And if that electron represents a source of energy and chlorine holds on to it, then that electron is no longer available as a source of energy. And that means we've had a reduction in available energy. So accepting that electron, gaining the energy or gaining that electron is not only a reduction reaction, but now we have to think of it as an endergonic reaction. Energy is being supplied to it in the form of that electron. And so not only are redox reactions gain and loss of electrons, but they're also about gain and loss of energy, which means they're a combination of an exergonic and an endergonic reaction, something that we talked about in the last presentation, that you frequently couple together an exergonic reaction to an endergonic reaction to provide the energy to drive the endergonic reaction. This has not changed here. We're seeing the same thing. So we'll talk about, I was about to put another note on here, but this one's getting pretty busy. We can add more notes about exergonic and endergonic reactions to later diagrams as we get to it. So let's talk, well, let me put it in here. And so we can put in here. Oxidation. And then down here, reduction. So a redox reaction is a coupled So again, we're applying ideas that we've learned in previous chapters. And again, this concept of coupling an exergonic and an endergonic reaction, we're seeing that here with a reduction and oxidation. So having got all of that out of the way, let's take a look at a reaction that involves molecules. So here is an example of a reaction that involves molecules. This is actually a burning reaction. And why would we choose a burning reaction? Well, remember again that cell respiration is all about combining something, glucose is what we think about primarily, with oxygen to give carbon dioxide and water. That's a burning reaction. So when you burn methane, which by the way is the main component of natural gas, when you burn methane, when you burn natural gas in the presence of oxygen, your primary products are carbon dioxide and water, just as we expect to see with cell respiration. So how does this become a redox reaction? Well, the way we have to think about this is to look at the electrons in the covalent bonds. So when we look at the electrons in the covalent bonds, when we look at the electrons in the covalent bonds of methane, we know that methane is a non-polar molecule because the covalent bonds are non-polar. The electronegativity of hydrogen and carbon are essentially the same. So they form non-polar covalent bonds. And in the oxygen molecule, well, the two oxygen atoms are identical, so they're identical in electronegativity. So the two covalent bonds that are formed here are in fact non-polar. So these electrons are in non-polar covalent bonds. So yeah, it's in red. And it turns out that electrons in non-polar covalent bonds are in relatively unstable bonds. So as soon as we start thinking unstable, we start thinking top of the playground slide. And when we start thinking about top of the playground slide, we start thinking about high potential energy. So electrons in non-polar covalent bonds, in molecules where there are non-polar covalent bonds, are relatively unstable and therefore represent a source of potential energy. Relatively speaking, they're in a high potential energy location. When we come over and we take a look at the products, carbon dioxide and water, the first thing we notice is we have broken the existing non-polar covalent bonds and we've formed some new covalent bonds. But these covalent bonds are no longer non-polar. These are polar covalent bonds. And if we ever doubted that, we just have to think about what we know about water. We know that the covalent bonds in water are polar. And that means that the electrons associated with these covalent bonds are relatively tightly bound. These covalent bonds are not going to break very easily because of the electronegative nature of oxygen. And so what we now have are electrons in polar covalent bonds. So the point here is that these electrons are no longer free to be given away because the oxygen in both water and carbon dioxide, being very electronegative, hold on very tightly to those electrons, comparatively speaking, because the difference in electronegativity between carbon and oxygen and between hydrogen and oxygen is quite large enough to trigger the formation of very stable polar covalent bonds. And of course, when you start thinking in terms of stable, you think in terms of bottom of the playground slide, and you think in terms of reduced potential energy. So in moving the electrons from a region of high potential energy, that is non-polar covalent bonds, to an area of low potential energy, that is polar covalent bonds, there has been a reduction in the potential energy. We've gone from a high potential energy situation to a low potential energy situation, which means there must have also been a release of energy. Because if you go from high potential energy to low potential energy, some of that energy has been given away, obviously, and some of that potential energy could be made available as kinetic energy to do work. So why does this also represent an oxidation reaction or a redox reaction? Because you've moved the electrons around. And we represent this in most chemical reactions where there's not a physical exchange of electrons, like we saw with the sodium and the chlorine, by a transfer of hydrogens. And you can see that actually happening here. The hydrogens that were associated with the carbon are now associated with the oxygens to form water. And carbon has itself become associated or has formed covalent bonds with oxygen. But the point here is that we've transferred the hydrogens that were associated with carbon away from the carbon and bound them up to oxygen. And that's how we physically moved the electrons from non-polar covalent bonds to polar covalent bonds. But it's been a loss of electrons. The electrons that are associated with the hydrogens are what have been moved. And they've been moved from carbon, from methane, that's where they've been lost from, to the addition of hydrogens to oxygen to form water. And along the way, they've been moved from non-polar covalent bonds to polar covalent bonds. And there's a very, very important idea that's tied up in this that helps you understand the chemical reactions as they're written, to realize that they are redox reactions. Because as I said, We don't normally represent the physical movement of electrons when it comes to redox reactions that involve molecules, because there's not a physical transfer of electrons as we saw with the sodium and the chlorine. It's all about repositioning them from non-polar covalent bonds into polar covalent bonds. And so there's not a literal transfer of electrons. And so the most important thing to remember here is that a hydrogen is equal to a hydrogen ion plus an electron. And so when we write these chemical reactions, these redox reactions that involve molecules, and we represent in the chemical reaction a transfer of a hydrogen away from one molecule to form another molecule, we need to bear in mind that that hydrogen is really showing the transfer of an electron along with a hydrogen ion to keep everything electrically neutral. And it's that transfer of that electron from a non-polar covalent bond to a polar covalent bond with its accompanying hydrogen ion, the equivalent of a hydrogen atom, that represents the transfer of the electron and therefore represents a redox reaction. The loss of the hydrogen, representing the loss of the electron, is the oxidizing side of the reaction. The gain of the hydrogen ion, representing the gain of the electron, or the gain of the hydrogen, representing the gain of the electron, represents the reduction side of the reaction. So when we see this movement of electrons from non-polar covalent bonds that are typically found in organic molecules to polar covalent bonds that are found in non-organic molecules. Because carbon dioxide, remember, is not an organic molecule. That is the movement of electrons from a high potential energy to low potential energy situation, but it also represents the movement of electrons away from one molecule to another molecule in the form of the electron accompanied by its hydrogen ion to maintain electrical neutrality. That represents that movement of electrons, the actual redox part of the reaction. I know that seems really complicated, but it's really important that you understand that, because that is the nature of redox reactions in cell respiration and in photosynthesis, because both of these biochemical pathways are a series of redox reactions. And once you can understand what a redox reaction looks like here, you'll understand what redox reactions look like both here and in cell respiration, not only in terms of the overall equations, because they represent a redox reaction, but also the individual reactions that we're going to look at in the various parts of cell respiration and photosynthesis as we break them down into their component bits and pieces. An extended explanation, but it's worth spending a little bit of time to explain that so that you really understand what's going on in these reactions, because ultimately this is the source of the energy that keeps us alive. Remember, the purpose of cell respiration is to extract energy out of food molecules so that it can be stored temporarily as ATP, and then that ATP can be used to drive cellular work in its many forms. And it's all about this manipulation of electrons through the redox reactions of cell respiration that makes that energy available to create the ATP that becomes that temporary energy store of the energy that we're extracting from food. So we don't want to lose sight of all of that in the complexity of the explanation, because that's what it comes down to as well. So when we look at the overall equation for cell respiration again, you start to realize why this is a redox reaction. So the glucose is becoming oxidized. So you have the loss of electrons from glucose as represented by the transfer of the hydrogen from glucose to oxygen to form water, What is left behind then is the carbon dioxide. So glucose is oxidized to carbon dioxide. Let me move the transcription box again. The oxygen then becomes reduced because that's where the electrons are going to. They are gained by the oxygen. And so you have this gain of electrons or gain of energy by the, as represented in the equation, by the gain of hydrogens by the oxygen to form water. But again, remember, it's all about the electrons. So those electrons that were lost from glucose are added to oxygen to give water. So the glucose is oxidized to carbon dioxide. The oxygen is reduced to water. There's our redox reactions. And remember, we are moving the electrons out of glucose, and they are primarily in the form of non-polar covalent bonds into the polar covalent bonds of carbon dioxide and water. And I'll put in here as well, hexagonic. Remember again, oxidation is exergonic, loss of electrons, loss of energy, and reduction is endergonic, gain of electrons, gain of energy. So let's take a look at what goes on in terms of moving electrons around. So where the electrons wind up is in a molecule called NAD+. So NAD+ is a electron acceptor, or an electron shuttle is usually the term that's used here, or an energy shuttle. All these names apply. So it could be an energy shuttle, an electron shuttle, an electron acceptor. And in the process of accepting those electrons, obviously it's going to become reduced. Gain of electrons, remember, is reduction. So the NAD+ is going to be the temporary home of the electrons that are going to be extracted. So we can expect that there are going to be a series of redox reactions that involve NAD+ and whatever it gets reduced to. So this is what NAD+ actually looks like, and you can see that it's related to the adenine nucleotide from RNA. And it's actually, nicotinic acid is actually one of the B group vitamins. So the term nicotinamide actually refers to the functional group that's obtained from one of the B group vitamins. So here we immediately start to see the connection between B group vitamins and energy production, which is what you'll probably learn a little bit more about in your A&P classes, should that be the direction that you're headed in, because that's where this becomes, that's the connection between the B group vitamins and energy production. We'll see this again in a couple of other places as well. But NAD+ is the key here, and its partner NADH. So you can see that there is a plus sign here on the nicotinamide part of the NAD+. That is where one of the electrons actually binds. So one of the two electrons that are going to be picked up by the NAD+ will actually bind and neutralize the plus charge on the NAD+. And in the process, it allows for the addition of a second hydrogen. And remember, a hydrogen is the equivalent of an electron plus a hydrogen ion. So the addition of the second hydrogen to the ring is the addition of the second electron. So we typically write the equation for this as NAD+ plus 2 electrons plus 2 hydrogen ions gives NADH plus a hydrogen ion. And the reason why we have 2 hydrogen ions, even though only one of them attaches to the NAD+, is because that's the way the chemistry pans out. And it means that we need an NAD+ on the right-hand side to make sure that everything that's on the left-hand side is on the right-hand side. In other words, we conserve everything. So this is the equation that goes on with the NAD+ and the electrons that are being extracted out of glucose. The vast majority of them are going to wind up being used to reduce NAD+ to NADH. But you notice that there is a bidirectional arrow here in the diagram. What that is telling us is that NADH, under the right circumstances, gives us this result. It gives up its electrons and becomes oxidized. And so this is how the NAD+ NADH pair act as electron shuttles or energy shuttles. The NAD+ picks up electrons in one location in the cellular chemistry of cell respiration and is reduced to NADH. And then in another location, it gives up its electrons and gets oxidized back to NAD+. And those electrons then can be used as a source of energy. You can't just move electrons around randomly. Because they contain potential energy, that means they're energetic, and that also means they're reactive. And unless you do something to keep them in a non-reactive form, but also in a high energy form, they're of no use to you for 2 reasons. Number one, they're going to give up their energy randomly. And number 2, that's going to do damage to cells. And so the NAD+ NADH pair serve as a way of transporting these highly reactive, highly energetic electrons that we're going to be extracting out of glucose from one location to another within the cell. And it allows us to retain the energy of those electrons without without running into the issue of having those electrons randomly react with something simply because they can. We want them to react in an appropriate way so that we can access the energy that they represent. And we want to do that in a very defined and very controlled fashion. So we store the electrons temporarily in the NAD+ NADH shuttle. So the NAD+ picks up the electrons from one location, gets reduced to NADH, shuttles the electrons, i.e. energy, to another location, surrenders those electrons, gets oxidized back to NAD+, returns back to the original location again to pick up some more electrons to shuttle them across to where those electrons are required. They act as dump trucks for electrons, picking up electrons in one location, dumping them off in another location, then coming back to pick up some more. So when they collect those electrons, they become reduced. When they dump off those electrons, they become oxidized again, or the NADH is oxidized back to NAD+. And you're going to see this play out in a number of locations in cell respiration. Ultimately, those electrons need to be pass through a process that will extract the electrons out of them. And this is where that cellular staircase that I was talking about comes into play. It's called the electron transport chain. The electrons pass down through a series of proteins that passes them from a high potential energy, low electronegativity situation to a high electronegativity, low potential energy situation. And of course, if you go from high potential energy to low potential energy, there must be a release of energy along the way. And because it's in a staircase fashion, the release of energy is incremental, and that incremental energy is then utilized indirectly to generate ATP. There is an intermediate step, as you'll see, but it is the incremental extraction of energy from those electrons via the electron transport chain that leads to the source of energy for generating ATP. And the vast majority of ATP that is produced through cellular respiration is produced through the combined action of the electron transport chain, the energy that it extracts out of it, and another series of proteins that are responsible for the direct generation of the ATP. The vast majority of ATP is produced that way. Not all of it, however. There is a small amount that is produced in an alternative fashion. And we'll see that alternative fashion in a minute. It's called substrate level phosphorylation. And you can see that it plays a role in the first two steps of cell respiration, because cell respiration is broken up into three separate steps that we'll investigate in the next section after we take a break. So in the next animation, because remember I'm breaking this up into multiple animations, so the next animation is going to cover the three steps in more detail. But the three steps are referred to as glycolysis, or known as glycolysis, which occurs in the cytoplasm or cytosol. This is the truly universal part of cell respiration. All cells that do cell respiration in some form or another do glycolysis. It is truly universal. All cells will do it. It can occur in aerobic respiration. It can also occur in anaerobic respiration. So it is truly universal. And it does result in a small amount of energy in the form of ATP, not a whole lot. If, however, you have a mitochondrion present and you have adequate oxygen, then the byproduct of glycolysis, a chemical called pyruvate, is transported into the mitochondria. It is groomed and enters into the result called an acetyl-CoA or acetyl-CoA, enters into a series of chemical reactions referred to as the citric acid cycle that results in the final chemical disassembly of the glucose. Glucose is partially disassembled in glycolysis, but it is fully disassembled, chemically at least, in the citric acid cycle. And again, the result is a small amount of ATP. But the true payoff is in this process referred to as oxidative phosphorylation, the third step of cell respiration, that involves the electron transport pathway and a process referred to as chemiosmosis. More detail to come, but this is where you get the vast majority of ATP being produced. Of the approximate 32 ATPs that are the end product of cell respiration, 28 of them, or around 28 of them, are the direct product of this process, of oxidative phosphorylation. So you can see why, in terms of understanding where the ATP comes from, the focus is right here. That doesn't mean we don't get ATP elsewhere. We do, obviously, but this is where the vast majority of it comes from. So where does this other ATP come from, the substrate level production of ATP? Well, as soon as we say substrate level, immediately you should start thinking enzymes, because remember, substrate relates to enzyme. And here it's the transfer of a phosphate on an existing organic molecule that acts as the substrate for the enzyme. It's the transfer of a phosphate away from that organic molecule to ADP to produce ATP. So enzymes in glycolysis. And the citric acid cycle. Can do this. This is where so this is where the ATP in glycolysis and the citric acid cycle come from. This ability of the enzymes in these two processes to actually transfer a phosphate group from an existing organic molecule onto ADP to create ATP. Doesn't make a lot of ATP, but for some organisms, as you'll see, particularly those that do anaerobic respiration and fermentation, this is all the ATP that they can make. If they're relying just on glycolysis, this is their only source of ATP. It's not much, but it's better than nothing. Okay, so time for a concept check, time break. I'm going to end this recording with this concept check. I'm not going to answer this question right now. I will provide the answer at the beginning of the next recording. So that will give you a chance to think about it before you start the next recording to find out the answers to these questions. So, which stages of cell respiration occur in the cytoplasm and which occur in the mitochondria? It was just on the previous diagram, so that should be easy. How do redox reactions make available energy from molecules? What is our understanding of how redox reactions can make energy available from molecules? I'll see you in the next animation.